Okay, welcome back to more integral stuff. This is section 5.3, which is called the fundamental theorem of calculus. This is actually my favorite mathematical theorem, so that's a fun fact. This is the theorem that tells us how to calculate a definite integral, what to do with those bounds. So I'm going to write it out because I think that's the best way to start. We'll talk about it a little bit and then we'll do a bunch of examples. So this is for certain a cheat sheet item. You can shorten fundamental theorem of calculus to FTC because mathematicians are lazy and we don't want to write all of that out. Okay, so this is the statement of it. I'm going to write it all out, then we'll talk. So we're going to let our function f of x be continuous on some interval a to b, and we're going to let capital F be any antiderivative of f on a to b. Then we have two conclusions actually. So the first one, this is like the most important one, is that the integral from a to b of f of x dx, remember, this kind of integral with bounds is called a definite integral, and the way you calculate that is you find that antiderivative. And it is important to note here that this is without that plus c at the end, so you just take the antiderivative as normal and then leave off the plus c because we're calculating a number, right? So we don't need a plus c. The plus c was for when we were calculating or constructing functions for our antiderivatives, and this time we're calculating an area, so that's a number. You don't need that plus c. So capital F is just the antiderivative itself, and then you plug in b, that top bound, and then you subtract that same antiderivative but plugging in a. And so there's notation for this, and I'm going to write that in green just because that's how I denote notation in my own notes. And it's written as that antiderivative capital F of x evaluated on a to b. So that's just the notation. These mean the exact same thing. This is just the more practical way of doing it, and this is more for organization. And then the second part of this theorem, which isn't as important in this class, and most people forget about it, is that the area function, which a of x, the area function, is the net area of the region bounded by the graph of f of x and the x-axis on our interval AB. And we can find that net area function by calculating the integral from a to some variable x of f of t dt. The reason we changed to t's is because we're trying to get an equation in terms of x, and the only way we can get an equation in terms of x is if we have different variables for our function. And remember, as long as we change this variable to match our variable of integration, it's the same thing as writing f of x dx. It's just that we're changing it so that we know we're going to be plugging in this variable x And so basically that will give you a function of area. Again, this isn't quite as important in this class, but it might be for those of you who move on to Calculus 2. And then you can take the derivative of that area function, the integral of a to x of f of t dt, and it's going to equal f of x. Again, this first portion is the most important part, so make sure you have that. The second part is more just showing you guys it. Oh, that was not successful. Showing you guys it so that if you see it in the future, you're not shocked by it. But like I said, it's not used nearly as much. It's not as important in our applications. I just wanted to make sure it's included so I'm not leaving anything out. All right, let's do about 1 million examples and then call it a day on this section. Okay, so examples till we die from them. The first example, we're going to calculate the definite integral from 0 to 10 of 60x minus 6x squared with respect to x. So this is kind of where notation gets weird. So first we just worry about what the integral is itself. So we know that we need to increase our power by 1. So this power over here is 1. 1 plus 1 is 2, so we end up with an x squared. And then we divide by our new power, 2. Then we're subtracting our 6 times x. X was originally squared. We're going to add 1 to that power, so we get a cubed. Divide by our new power, which is 3. And then evaluate it from 0 to 10. So that's where, up here, I wrote this bar evaluated from a to b. I actually like to have square brackets around my entire antiderivative so that I can tell that I'm plugging in these numbers into both this part and this part. So some people just do it like this, but then they add a bunch of parentheses, and I prefer just to do square brackets to kind of keep things neater and remind me what to plug in where. Okay, so this is our notation, this is our antiderivative, these are our bounds. Now we're going to use the fundamental theorem of calculus, which means we plug in this top bound first, so this 10, and then subtract what we get when we plug in the bottom bound 0. And that looks like this. So we get 60 times 10 squared over 2. That's me plugging this 10 into this x. Minus 6 times 10 cubed over 3. Again, that's me plugging in this 10 into this x. And I'm going to put parentheses here because when in doubt, parentheses it out. And then I subtract what I get when I plug in this bottom bound, 0. So I'm going to put in another parentheses, so I remember to distribute this negative. And I'm going to get 60 times 0 squared over 2 minus 6 times 0 cubed over 3. Okay? So that is our actual answer, but we're going to simplify it. We get 60 times 100, which is 600. Nope. 6,000 over 2 minus 6 times 1,000, which is also 600, or 6,000, sorry, over 3, and then minus 0, because if you look here, both of these are multiplied by 0 in the numerator, so we just get 0 minus 0, which is 0, and so that guy becomes 0. And when we simplify these fractions, we get 3,000 minus 2,000, which is 1,000. And that would be your final answer. Okay, so that's an example using a polynomial. Next, we're going to do something a little bit more complicated. That's how my examples usually go. Hopefully you're used to that by now. So for example 2, we're going to do the integral from 1/16 to 1/4 of the square root of t minus 1 over t dt. And remember, the t's are just the same as x's as long as our t in here matches our t in the dt. We're going to rewrite this before we take the integral. So this is the integral from 1/16 to 1/4 of, so remember that the square root of t is technically t to the 1/2. And then when we have powers of t in the numerator and powers of t in the denominator, we just take the power in the numerator minus the power in the denominator. So this is t to the 1/2. And then this is t to the -1. So 1/2. Sorry, this is t to the 1. And so we take 1/2 minus 1, which is -1/2. So we end up with t to the -1/2 minus, I'm going to leave this as 1 over t, and you guys will see why. I could technically write t to the -1, but it's more recognizable if we leave it in this form. So I hope you guys agree with me that these are the same thing. That's just algebra, but I know algebra is challenging. So before we dive in, we know how to deal with this first bit, the t to the -1/2, because we just increase this by 1, so -1/2 plus 1 is +1/2, divide by our new power of 1/2, and then we're going to subtract the integral of this guy. But if we were to do that like normal, we would have t to the -1, and increasing that by 1, increasing that power by 1 becomes t to the 0 divided by 0, and we know we can't divide by 0. So something's off there. And I want you guys to remember when we were talking about derivatives, we knew that the derivative with respect to x of the natural log of x was equal to 1 over x. And we know the antiderivative is the same as an integral, and it just undoes the derivative. So if we have 1 over x and we're trying to take the antiderivative of that, we should be getting the natural log of x. So we end up with, oh, I don't know why I still have my bounds. I already took the integral. Sorry, those shouldn't be there. This should be a square bracket. And then the integral of 1 over t becomes the natural log of t. It is important to put the absolute value of t, because if your bounds were negative, it wouldn't actually be defined. The natural log isn't defined for negative numbers. And then you need to write our bounds, which are 1/16 to 1/4. Okay, so now we plug it in using the fundamental theorem of calculus. So we first plug in the 1/4 because that's our top bound. So we get 1 over 4 to the 1/2 divided by 1/2 minus the natural log of the absolute value of 1/4, but the absolute value of 1/4 is just 1/4. Big parentheses, and then we're going to subtract and plug in the 1/16 bound because that's our bottom bound. So we have 1/16 to the 1/2 divided by 1/2 minus the natural log of 1/16. Okay, so this looks gross, but we're going to simplify it. Technically, remember, you guys can use Symbolab. If you struggle with your simplification, maybe try it on your own and then double check using Symbolab. Again, that's the word symbol and then just ab.com. It's not 2 L's. It's a really helpful calculation tool. It makes things easier to type out as far as a calculator goes. So you could do that, but we're going to do some quick maths just for fun. The square root of 1/4 is 1/2. And then the natural log of 1/4 we're going to leave for now. Then we have minus the square root of 1/16 is 1/4. Plus, because we have a negative times a negative, that's why I like to have those parentheses so I remember to distribute, the natural log of 1/16. So 1/2 divided by 1/2 is just 1, minus the natural log of 1/4, minus 1/4 divided by 1/2. You can either think of it as 1/4 is half of a half, or you can think of it as 1/4 times the reciprocal of 1/2, which is 1/4 times 2, which is 1/2. So we have a negative 1/2 here, plus the natural log of 1/16. And we're going to combine like terms. So we have 1 and negative 1/2, which becomes a positive 1/2. Then we have the natural log of 1/16 minus the natural log of 1/4. And I don't know how much you guys remember about logarithm rules. I think they're kind of fun. You guys might not. But the natural log of something minus the natural log of something else is the same as the natural log of the one that was positive divided by the one that was negative, which we can simplify to 1/2 plus the natural log of 1/4. Okay, so that would be your final answer. You could have just plugged in what we got up here into Symbolab or some other calculator and gotten it. I just think it's interesting to look at the algebra sometimes. All right, let's do one more example and call it for this section. Then there's only one more section and you guys are done with calculus, which is exciting. Or sad, depending on your viewpoints. Okay, so our final example, we're going to take the integral from 0 to 2 pi of 3 times sine of x dx. So first of all, from the rules we talked about, we know we can pull this 3 out front and make it from 0 to 2 pi, the integral of sine of x dx. Sorry I'm coughing so much. I went on a terrible run. So this is another one of ones that you can't use the power rule for integration because sine of x is not a polynomial, but if you think back to the rules we remember for the derivative, we know that the derivative of cosine is negative sine of x, which means that the derivative of negative cosine is sine of x. So that means the antiderivative, aka the integral, of sine of x is negative cosine of x. Okay, so we can use that in this problem. So we're going to get 3 times, using our brackets because the 3 is on the outside, and we're going to be plugging in our bounds on the inside. We just said that this integral of sine of x dx is negative cosine of x. We don't need that plus c because we have our bounds from 0 to 2 pi. So we're going to get 3 big parentheses here because we're going to be distributing that 3 to everything. Negative cosine of 2 pi, plugging in that top bound first, and then subtracting negative cosine of 0. So we end up with 3 times the cosine of 2 pi is 1, so we have a negative 1 here, minus a negative, so that's plus the cosine of 0 is also 1. So we end up with negative 1 plus 1, which is just 3 times 0, which is 0. And this should kind of make sense if we were to draw a picture of 3 times the sine of x. It's going to look like this, where our amplitudes are 3 and negative 3. And we know that this area is the same as this area because sine is a, oh god, I forgot the word, periodic function. And we end up with a positive area up here and a negative area up here, and so they cancel each other out. So the 0 makes sense here. All right, that is it for the fundamental theorem of calculus. Hopefully that's a good amount of practice. I really, really encourage you guys to do your homework on this one, regardless of whether or not you have 100% in the online homework, just because it's easier to remember the fundamental theorem of calculus, or just like the rules for integrating a definite integral, the more you do it. All right, see you guys in the next and the last section.